Well, thank you, Sam, and thanks to all the other organizers too. So my plan is to go till about 20 past the hour, and I think if you have like a quick technical question, maybe it can be answered in the chat. Otherwise, the people watching that will interrupt me. Okay, so I'm going to talk about practical Quasi-Monte Carlo sampling, and I'll tell you what Quasi-Monte Carlo is. I'll show you why it's way better than Monte Carlo when it is way better than Monte Carlo. And I want to steer a balance between overselling QMC and underselling QMC. So, sometimes there are very strong claims made. Somebody's defeated the curse of dimension, and I don't quite believe that. And then you can undersell it by looking at worst cases that simply, don't happen. So there's a middle ground. And the other thing is to make it really, really, really work involves a mixture of good luck and hard work. Okay, so by practical, I'm going to touch on the theoretical results that I personally find the most useful. And most of the references for this talk are in these online notes, and I believe that they're linked to from the seminar webpage. So I have a few chapters of my Monte Carlo book on practical Quasi-Monte Carlo. So most of the references from today's talk are in there. And let me apologize, I'm giving you about 1% of the subject. So I've cherry-picked the parts that I like, but there's a lot more. There wouldn't be time to put everything in one talk. So the problem we're trying to solve is to compute an expectation. Or we could think of it as computing an integral. And you can translate between those. Most of Quasi-Monte Carlo was formulated as an integral. It probably started as an expectation. And in many cases, well, let's go back up here. We want the expected value of f of x, where x has some distribution p. And very often there's some transformation psi. And if you put a uniform random vector into psi, then you get some x that has the distribution p. So often, not every time, but very often, there's a transformation like that. So you can turn uniform random numbers into things that have the distribution p. They don't even have to be vectors. It could be whatever they want to be. Anything that you can Monte Carlo if there's this transformation psi. Now, we used to get those from the book of Luc Devroy, sometimes called the Bible of non-uniform random number generation. In recent years, people are looking at how to use normalizing flows to either get or approximate this transformation. Okay, so now the thing that we want to compute is an integral over the unit cube of this function f composed with that transformation. Okay, so we've turned the problem into this problem, and we might as well absorb that transformation right into f. Okay, so our new f is our old f composed with the transformation. So now it's all about how do we integrate something over the unit cube? Okay, well, if you're going to integrate over a high-dimensional unit cube, there is a cursive dimension for that, and there are lower bounds on how well you can do it. What you might do is take a plain quadrature rule like Simpson's rule, and Simpson's rule, if you have 4 derivatives, you get n to the minus 4 error in one dimension. But if you use it in d dimensions, you get n to the minus 4 over d. And it doesn't really help you to have a lot more derivatives. Nobody can really make proper use of like a billion derivatives. So you're stuck with this kind of a curse. There's a lower bound on how well you could do. Somewhere there's a function out there that would mess up your points. And this is why Monte Carlo is so popular. In Monte Carlo, all we do is we take IID draws from that distribution, plug them into F, and average them. Okay, so if that integral even exists, then the strong law of large numbers tells us this is going to converge. And if the integral has a finite mean square, if it's in L2, well, then we're going to get an error that's n to the minus a half. And we get that for any dimension d and any smoothness r. So that's a huge win over n to the minus r over d. These up here, this is a lower bound that comes from a deterministic point. Here we're using random points. That's how we can well, that's how we can at least mitigate the problem of high dimension. The n to the minus a half rate doesn't seem like it's that great, but at least it's not like n to the minus something over dimension. Well, what we're going to do is take this integrand f and push points into it and then average them. And so we have a lot of choices for what we can put into that function. If you use the product rule of Simpsons, or you're using basically Fubini's theorem, then you could just push a grid of points through. And that's obviously going to be very bad in high dimensions. Sometimes you can't even do 2 to the d. Or you could use plain Monte Carlo points. If you're using plain Monte Carlo points, well, they'll be different every time, but here they're clumping up in one place. There's a big hole that they've left behind. So it seems like we should be able to do better than this. Quasi-Monte Carlo points are trying to do better than this. The next 4 are Quasi-Monte Carlo points. So this is a Quasi-Monte Carlo, that's a Quasi-Monte Carlo, and so are these. In the 2016 MCQMC conference, we even had a contest where people were asked to identify what these different kinds of points were. So those 4 are Quasi-Monte Carlo points. This is a sparse grid. I won't be discussing that today. And these are what are called blue noise points. They're popular in computer graphics. These points have a couple of things going for them. They want to be uniformly spread out. They don't want to be too close to any other point. So they have this sort of penny packing, self-avoiding property. And you could really self-avoid on a grid or a hexagonal grid or something, but that would be bad in a Fourier space and it would make your picture look bad. So they don't want to do that either. So the graphics people have a lot of special ways to pick points to go into the function f. The main Quasi-Monte Carlo constructions fall into 2 classes. They're digital nets and similar. The famous example are the Sobel points. So if you've seen people using Quasi-Monte Carlo points, a very good chance they were telling you about Sobel points. There's a whole other branch of the field that uses lattices. And the best one is the Fibonacci lattice. Fibonacci lattice only works in 2 dimensions. So once you get to 3 or higher dimensions, it is a little bit of a chore to pick the lattice you're going to use. So it's less convenient. And I'll just emphasize the digital nets. A lot of people work with lattices, though, and there are times when they work quite well. Okay. What we want to do is make the uniform distribution on the endpoints that we picked as close as we can to the uniform distribution on that cube. So this is a discrete uniform, and that's a continuous uniform. Let's line them up to the best of our ability. Okay, so that means we have to minimize the distance between, say, a sample uniform and a population uniform. There's actually a lot of different ways to say what's the distance between a discrete and a continuous distribution. Those are called discrepancies. It's a classic topic. It goes back to Weil and just over 100 years ago. How close can you actually get with your discrete points to some continuous uniform distribution? And it's a fundamental thing in computational mathematics. So we'll often start off posing some problem in continuous mathematics. Then when the time comes to solve it on a computer, we've got to use some kind of discrete computation. So we're always, or in that setting, we're always trying to approximate some continuous thing with some discrete thing. And so we want the discrete thing to be close to the continuous thing to the extent that we can make it. So here's an example, the local discrepancy. So in this box, there's a bunch of points in this square. And I've highlighted for you a subset. It's called an anchored box because it's a rectangle that goes from the origin up to some point A. And this box has a width of 0.3 and it has a height of 0.7. So it has an area of 0.21. So it's got 21% of the square. It deserves 21% of the points if it's got 21% of the square. Well, let's look at how that works out. So here's this, what we call local discrepancy function at the point A. And it's a fraction of those points that are in the box minus the volume of the box. So it's like a sample minus a population volume. So the sample volume minus a population volume. Well, let's look at the sample volume. That box got 12 out of the 50 points. So it got 24% of the points. But it actually deserved only 21% of the points. So it's got a local discrepancy of 3%. It's slightly oversampled. Okay, now the star discrepancy is an L infinity norm of the local discrepancy. We find the worst box. So find the anchored box that got the worst discrepancy, worst absolute discrepancy. So this is the star discrepancy. It's a function of your endpoints. And this is the most commonly studied discrepancy measure. It has this weird fixation with the origin, and there's a lot of other measures that don't bother with the origin. And some people will take an L2 measure instead of an L infinity. There's a lot of different ways to talk about the discrepancy. The reason this one is so central, it's the Cox-Mihalkovitch inequality. So here is the integral that we want, and here's the average that we have. And we introduce this thing called the total variation of f, so VHK of f. So it's the total variation of f in the sense of Hardy and Krause. Now, it generalizes total variation from one dimension. When you get to the multidimensional cube, there's 12 or so different ways to say what's the total variation of a function. The one by Hardy and Krause is the one that everybody likes to use. The error that we're going to make, our absolute error, is upper bounded by the star discrepancy that says how non-uniform our points are, times the variation, which is how non-constant our function was. So it very conveniently splits into two problems. And then all you have to do is try to reduce this. And we can actually do a pretty good job. We can make the star discrepancy essentially log n to the d minus 1 over n. So we can get a star discrepancy that's basically going to be better than Monte Carlo. It's going to be much smaller than n to the minus a half. So that's really nice, except for all those logs. Oh, and then there's another thing. Some integrands actually have unbounded variation, and we were going to be able to get those too. And then this inequality doesn't really help us study that. Okay, so it's nice. I mean, except for all those logs, it's really nice. So what do people do with the logs? Well, sometimes what they do is they just note, 1 over n times log n to the d minus 1. That's actually big O of n to the minus 1 plus epsilon. And that's true for all epsilon. And is that actually realistic or useful? Well, I mean, it's true. Any power of log n is little o of n. But it's not that great because, log n to the 99 over n is really not negligible for any reasonable n. In fact, log n to the d over n increases until you get to the, e to the power d. Okay, so yes, it's reasonable, but no, it's not reasonable. But yes, it is reasonable because this bound is for worst case functions that are quite implausible. Nobody has ever seen that happen. Recent paper with Sex and Pan, where we basically ask, well, where are those log powers? And nobody sees them in applications. We prove that there are functions that have it. We couldn't even construct something that needed log n squared. So I think you're safe. And later we're going to get rid of them anyway, because we're going to randomize the points to kill off the powers of log n. Okay, so where does Quasi-Monte Carlo get used? I think the biggest use is in graphical rendering. So computer graphics, and there's a lot of people that have worked on that. I'll point to Alex Keller, but there are many people that have done that. And they, okay, so it's used in lots of rendering. They actually got an Oscar. So there was an Oscar for Quasi-Monte Carlo, the company Mental Ray, which is now part of NVIDIA. They got an Oscar because their methods were used in lots and lots of movies. They're used in special effects and some post-production. Alex tells me that it's starting to be picked up in computer games. So those people working in Hollywood give the coolest talks. They don't get necessarily a lot of citations for it, but I think most of us would trade a bunch of citations for an Oscar. So that's, that would be pretty good. There are a lot of other places where Quasi-Monte Carlo gets used. Actually, I think there should be more other places. One of the early adopters was computational finance, valuing a stock option. There's a lot of work on solving partial differential equations in random environments. I'm quite excited about some new work. So there's work in variational inference. So Sifan Liu and others are finding ways to use Quasi-Monte Carlo to solve the sampling problems there. And Bayesian optimization, Max Ballandat reached out to me to ask for a strong law of large numbers for randomized Quasi-Monte Carlo, and they needed it in Bayesian optimization. However, I feel like there should be more uses of QMC where it makes a difference. Okay, so I want to give you an example of how Quasi-Monte Carlo can fill out space better than Monte Carlo. And I'll start with the van der Korput series. So what we're going to do is we're going to make xi for the integer I. So the integer I, our sample number goes 1, 2, 3, 4, 5. It just keeps increasing. And van der Korput writes it in base 2. Okay, so 5 is 1, 0, 1. Okay, so here they are written out in base 2. Then van der Korput reflects those in the decimal point or binary point, if you would prefer. Okay, so 1 goes to 0.1, 110 goes to 0.001. Okay, so they just get reflected. And then what's 0.1 in binary? Well, that's a half, or 0.5. And then what's 0.01? That's a quarter, 0.11, 3/4, and so forth. And what you notice is if you asked somebody naively to put points in the unit interval as fair as possible, if you told them to put 1 point, they'd put it in the middle. And then if you say, well, you better add another point, what are they going to do? The interval is now 2 intervals that are empty. They'll either split the left one and then split the right one, or maybe the other order. Okay, fine. Now there's 4 intervals, and the next 4 points go in the middle of those 4 intervals, and it goes on like that. And so this fills up the unit interval pretty evenly. And we can see why. If you take an integer, it alternates between odd, even, odd, even, odd, even. Well, the odd ones go on the right half, and the even ones go on the left half of the interval. So you go right half, left half, right half, left half. So wherever you stop it, you've got about half the points to the right of 0.5 and about half of them to the left. And if you look at 4 in a row, every consecutive 4 puts 1 in each of 4 equal-sized subintervals, and so on for 8, 16, or whatever. And so it fills up the interval very nicely, and the star discrepancy is known to be law of order log n over n. Now, in mathematical descriptions, we usually make the first point 0, not 0.5. Okay, so Halton took advantage of this, and he used the van der Korput trick for any base. And he'll use bases 2, 3, 5, and 7. He'll use consecutive primes. There's a sense in which the primes are orthogonal to each other. It's like the Chinese remainder theorem. So here's how Halton goes. He writes the integer I in base B. So here we have it, say it's in base 5 with increasing powers of 5. And now you flip it to have decreasing powers of 5, and now it's a point in the unit interval. And then he puts together base 2, 3, 5, and so forth. And here's how it looks. If we have just 2 dimensions, base 2, we could take 8 equal bins, base 3, we could take 9 equal bins. That's 72 bins. Every consecutive 72 points puts 1 in each of those bins. And so here's how it is with, a few more points, and here's a comparison with random points. Okay, so Halton is a nice space filling thing. It has a little bit of a problem, like, if your prime is base 101, then the points start marching along a stripe from the origin to the far corner. But those can easily be fixed by scrambling. So Halton's kind of the first thing you could do. You could make it an exercise in a Monte Carlo course, and then scrambling it is necessary. Okay, now I'll show you how digital nets work. They're like Halton, except they use the same base in all the variables. Okay, so what's going to be our goal? Well, we'll take the unit cube and we'll break it up into tiles. And so here I'm breaking it up into tiles in base B, and this B is 3. And I can split it 3 ways this way, 9 ways, 27 ways, or I could split it 3 ways that way, 9 ways, 27. If I've got 9 points, I would love to have 1 in each of these stripes, 1 in each of these squares, and 1 in each of those. That might remind you of Sudoku. Or if I had 27, I'd like to have 1 in each of these, 1 in each of those, 1 in each of those, and 1 in that. And if I had 4 variables, I would like those things to be true if I made the tiles out of any 2 of my 4 variables. Or if I had 3 variables, I would like a 1/3 by 1/3 by 1/3 tiling to get 1 point each. And this is what digital nets will do. They're going to find a way to put the same exact number of points in every one of these tiles of a given volume. So that's what digital nets do for you. That's how they get to be so much more uniform than Monte Carlo. And the number of tiles that they balance grows faster than the number of points you use. Okay, so what's called a TMD net in base B, the M is we have B to the M points. The D is the dimension. And T is that every tile that deserves B to the T points gets B to the T points. We'd love to have T equals 0, and then every tile that deserves 1 point gets 1 point. But sometimes the best you can do is every tile that deserves 8 points gets 8 points. Okay, so here are some pictures of digital nets in base 5. These are from the construction of RE4. And so here we have B equals, or M equals 3, so that's 125 points. And you can see that, wow, every one of these little 1/5 by 1/25 tiles gets its point that it deserves. And what you cannot as easily see is there's 125 equispaced bins along this axis that all get 1 point, and the same along that axis. And if you take any 3 of the variables, the 1/5 by 1/5 by 1/5 tiles all get balanced. Okay, so that's the construction of RE4, and here it is with 625 points. Next up, after a TMD net, there are TD sequences. So a TD sequence will take a net, and then we'll take another net, and another net, and another net. And we have this infinite stream of TMD nets. And they have this beautiful property that each of them fills in the holes that the other one left behind. And so if I take B of them in a row, I actually balance up to 1 degree finer. So M goes to M plus 1. So instead of B to the M tilings being balanced, it's B to the M plus 1 tilings are perfectly balanced. And this is true recursively for all M. Okay, so those give you infinite sequences. And the famous one is the one of Sobol, which has base 2, but he can't always get T equals 0. And the other one, RE4 was able to get T equals 0, but he has to have B a prime number at least as big as the dimension D. Okay, so Quasi-Monte Carlo is deterministic. So if you want to estimate your error, you're kind of out of luck. You know that your error is below the product of these 2 quantities, but you just can't compute those 2 quantities very well. So now we introduce randomized Quasi-Monte Carlo. In randomized Quasi-Monte Carlo, every x is uniformly distributed. Okay, so now you're going to have an unbiased estimate. But collectively, they have small discrepancy. So now you're going to get an unbiased estimate with quasi-Monte Carlo accuracy. So you kind of get the best of the Monte Carlo, quasi-Monte Carlo worlds. So now what do we do? Well, we just do it like 10 times independently and pool the answers. And now we have a variance estimate. So now we can estimate roughly what our accuracy is. How are we going to make that thing? How are we going to randomize it so that every point is uniform, but collectively there's still low discrepancy? So one of the methods is nested uniform scrambling. So here's a three-dimensional cube. If we had a quarter of our points in each of these slices, and then we just shuffled them in random order, we'd still have a quarter of the points in every slice. And then if we took one of those slices and cut it into 4 pieces, if those 4 pieces each had a quarter of the points and we slice them and scramble them, they're still balanced. And so then we'll just do that we'll take all 4 of these, slice them into subslices and scramble. And then we just carry that on recursively. And you can go until you reach machine precision, or more easily, you go until there's only 1 point in the slice, and then you place it at random. Okay, and then you do it vertically, and then you do it in the depth. And while I'm shuffling these points in this direction, if the top quarter had its fair share of points, when I shuffle them, the top quarter, nobody left or entered the top quarter, so it still has its right balance. Now imagine sitting on your favorite point. After the first round, you're equally distributed on the x-axis into one of these 4 bins. And after the second round, you're equally distributed into one of 16 bins and so forth. So you end up uniformly distributed if you're just 1 point, and you end up still balanced if you're multiple points. And there's a partial G randomization of this due to Matusek that's very useful. It takes less storage. Okay, so what do we get with these scrambled nets? Well, first of all, they're unbiased. Second, if the function has finite variance, then the scrambled net variance is going to be little o of 1 over n. If the function is smooth, all the mixed partial derivatives are in L2, mixed partials up to order 1 per dimension, then the variance has this n to the minus 3 plus epsilon flavor. Okay, so you can be much better than plain Monte Carlo if the function is smooth. What about those darn logs? Well, if the function's in L2, your variance can't be more than some multiple gamma of the Monte Carlo variance. Okay, so there's no room in gamma for that to be like log n to any power. And then a newer result with Daniel Rudolph, if you have 1 plus epsilon moments, then there's a strong law of large numbers. Okay, so let me go through an example. So this is an example from a paper with Kathlish and Morikoff. And the function f is the value of a collateralized mortgage obligation. It's a 360 dimensional integral because with 30 years and every month the interest rate could change. And if the interest rate goes down, then people might pay off the mortgage and refinance. And if the interest rate goes up, then they're not going to do that. And so there was a model of how people respond and what should you pay for this mortgage obligation. In some of the complicated cases, the pool of mortgages were all diced and sliced into various tranches. So it's pretty hard to figure out what's going to be the value of that thing. And a Monte Carlo, is a very straightforward way to go. And then Quasi-Monte Carlo can help there. This article somehow, it's from the only volume that's no longer present at the journal's website. I don't quite know what happened there, but there is kind of a problem that things in the journals don't necessarily stick around. Okay, so the model is driven by Brownian motion. It's actually geometric Brownian motion, but inside there's a regular Brownian motion. And so how do you make a Brownian motion? Well, what you can do is you can say at time t, It's whatever it was at time t minus 1 plus a Gaussian increment. And this is a standard Brownian motion, so it's the square root of the time step. Okay, so all we do is we just get 360 Gaussians and add them up, and then take cumulative sum, and that'll get us a Brownian motion. There's another way to go called the Brownian bridge construction. And it exploits the fact that you can generate a multivariate Gaussian in like any order that you like. So the first thing you can do is use one Gaussian to figure out, well, where does the Brownian motion end up? And then conditional on where it ends up, where was it halfway through? And then conditional on where it ended up and where it was halfway through, where was it at time a quarter of the way through and 3/4 of the way through? It's basically the van der Korpet trick all over again, but in the time interval. So you can generate the Brownian motion in that order. And then there's a Markov property that makes that extremely doable. Okay, so, well, here's how it looks. So what we'll do, the first thing that we do is we figure out, well, where is it at the end of the time period? And so a simple approximation would be say, I think the Brownian motion kind of is going to go along this line. And then after you've generated 8 points, 8 observations, you have the skeleton. So it goes from here to here to here. And that skeleton tells you most of what's going to happen to that Brownian path. The next 352 variables, they just fill in these local fluctuations around the skeleton. So this Brownian bridge construction packs the importance. Most of the importance goes into the first 8 variables. I mean, much of it goes into the first 4, a lot in the first 16, but it's crammed the importance into the first few variables. Okay, so that wouldn't make any difference for Monte Carlo, but it makes a difference for Quasi-Monte Carlo. So let's see, Quasi-Monte Carlo, how do you generate your Gaussian? In Monte Carlo, what you do is you take a uniform variable, you can take a Gaussian inverse CDF, you can take a Kleski or another root, multiply, and then you can add the mean. And you can use any matrix square root, and it won't change your Monte Carlo accuracy. It might change your computing cost, but it won't change your Monte Carlo accuracy. But Quasi-Monte Carlo is different. The accuracy will be strongly affected by the particular square root you pick. So what are you going to do? Well, you could use the Brownian bridge. That goes back. Moskowitz and Kaflish used it, and I think I found something in the 1960s where Sobel was using it too. Or you could use a principal components construction. So that you can use principal components in non-Brownian cases. Like any covariance matrix has principal components, so you could sample principal components. If you're going to do principal components, you're kind of stuck if the covariance would be the identity matrix. Then everything's a principal component. So I have a paper with Sifan Liu where we use active subspaces to try to find the covariance, the square root to use. Okay, so here are the results. So there were, okay, so the figure comes from the Journal of Computational Finance, Volume 1, Number 1. That number is no longer available on the internet. Hopefully it comes back. For this integral, you know exactly what's going to happen with Monte Carlo. Here is the sample size, log scale. Here's the error, log scale. Both of them are log 10. And if you know the Monte Carlo variance, then you just know exactly what's going to happen. And so that's going to be the Monte Carlo root mean squared error. For that integral, if you use antithetic sampling, you would drop the Monte Carlo variance down to this. Okay, so antithetic sampling would be better. If you use quasi-random sampling, you would get this better rate. Actually, it doesn't start off better, but it ends up getting better. How much better? Well, basically 2 ticks on this axis. So it's like the error is about 1/10 by the time you get to these quite large sample sizes. Okay. So I mean, 1/10, you do see a better slope. 1/10 is nice to have. In those days, people really wanted more. Also, you can see if you mix quasi-random with antithetic sampling, it doesn't do much. And the reason it doesn't do much is that the quasi-random points are already kind of antithetic. If you haven't seen antithetic, it's every time you get a uniform variable, you use 1 minus that same uniform variable, its complement. And if you push that through a Brownian motion, every time you get a curve that squiggles, you get a reflection in the origin and a curve that this second curve zigs where the first one zags, and so you can balance things off. But the antithetic points are already the quasi-random points are already kind of antithetic, so it doesn't necessarily win you that much. They're already antithetic, especially in their one-dimensional projections. Okay, but now let's try the Brownian bridge. So here are the curves from before, and let's see. If you do Latin hypercube sampling, you also get the same improvement that antithetic sampling would have done. Here's quasi-random with the Brownian bridge. Okay, so it's much better, and it's showing a better rate of convergence compared to Monte Carlo. And then here's randomized quasi-random. So if you take the quasi-Monte Carlo points and randomize them like I described, then the error goes down, even the convergence rate improves. And let's see, quasi-random with antithetic sampling. And I don't know why we don't have RQR with anti, but anyway, those are, okay, so this is a pretty dramatic improvement, especially compared to plain Monte Carlo. And so that's the case of a big win. And then it was either hard work to figure out, oh yeah, you should use the Brownian bridge, or maybe a bit of luck to find out that the function needed it. That paper introduced the notion of effective dimension, or one of the ways we call effective dimension. And with the Brownian bridge construction, the first function that came up was 99.96% additive in terms of R squared. Okay, so if your function is basically a sum of functions of one variable at a time, and you only need to sample them one-dimensional margins. And we thought that's just too easy. So we changed the function from the finance problem, we made it harder. So we made it much less additive. This one is 0.04% non-additive. This is like 150 times as much non-additivity. Okay, so that was the example that I showed you, was the more difficult function. And then we have this notion of effective dimension, and it's based on the analysis of variance. Efron and Stein made a major contribution, and then it goes back through the 20th century. The analysis of variance writes your function as a sum of functions that don't depend on all the variables. So the function indexed by u only depends on the xj, where j is in the set u. Okay, so there's lots of different ways to decompose a function this way. The ANOVA is the one you might be most familiar with, and it pushes importance down to the low cardinality where possible. Okay, well, if the function has this sum, we can just apply Cox-Mihalka term by term. And so now our error is upper bounded by this. And if the cardinality of u is small, then the star discrepancy is small, because Quasi-Monte Carlo is really good at the 1, 2, and 3-dimensional margins. And if the function is well behaved, if the cardinality and the cardinality u is large, then there's hardly any variation. So the way it works is either this one's really small or that one's really small. Okay, so if you have some low effective dimension where the function is dominated by its low dimensional parts, then this kind of decomposition shows how you can benefit from QMC. And we said that your effective dimension, you can have a d-dimensional function that's effectively dimension S. And in one sense, if the first S variables are 99% of the variance, then it's really effectively an S-dimensional function in a truncation sense. Okay, so that if that skeleton captures most of the Brownian bridge, then maybe it's effectively an 8-dimensional function because the other 352 don't really change anything. And I think more appropriately, there's a superposition sense. If interactions up to order S already capture 99% of the variance, then really it's an S-dimensional function. You don't have to do things 360 at a time. So the huge gains from QMC come from reducing effective dimension. And there's no automatic procedure that will always do that. Okay, so I want to show you a little bit more about how the variance gets to be little o of 1 over n. So instead of the ANOVA decomposition, we're going to write our function as a sum of piecewise constant functions. And it's piecewise constant within tiles. So, of course, you can have a constant over the whole space. Then you can have something that's constant within these tiles, but orthogonal to that tile, and constant within these 16 tiles, but orthogonal to all the other ones. Okay, so there's an ANOVA, there's a decomposition into an infinite list of piecewise constant functions, constant within tiles that get finer and finer and finer. Now, what can happen is that, let's see, because these are orthogonal, the randomized QMC variance ends up to just being a sum of contributions from each of these tiles. So sigma k squared is the variance of, say, the function that's constant within one of those tiles. Now, if the function is smooth, then the coarse and low order tiles dominate, and the very, very fine ones, they're like derivatives of derivatives of derivatives, and they end up being kind of small. So, derivatives times volume. So you can write the variance of your estimate as 1 over n times a weighted sum of these variances. And then these coefficients here are called gain coefficients. If they would be all 1, then we'd get the Monte Carlo variance. Now, what happens in a digital net is that the contribution from this set of tiles, eventually it's 0 because you balance that tile out, those tiles, and you integrate it perfectly. And the only thing that can go wrong is like maybe one that you didn't balance has more than Monte Carlo variance. But it's bounded how much more than Monte Carlo variance it can have. Okay, so you can write it as this sum. All of these individual coefficients converge to 0, and the biggest one is bounded. And so the variance is going to be little o of 1 over n. And how do you get that? You can use Haar wavelets, and you can use Haar wavelets in base B, or you can use Walsh functions. Okay, so then you get this variance formula. Combinatorial arguments will show that you balance everything. Eventually, the gammas all go to 0, and it's a trickier combinatorial argument to bound the soup. Okay, so n times the variance goes to 0. There's no powers of log n. Okay, so software, there's now some quite good software to do randomized and unrandomized Quasi-Monte Carlo. I'll give a shout out to Fred Heckernell's group. They developed the guaranteed automatic integration library. Their focus is you tell them epsilon, and they're gunning for an error estimate where the error is below epsilon. You need assumptions to do that, but if you decided that you know the accuracy you need, then they have tools to give you that. They've also more recently developed QMC Pi, so Python software for Quasi-Monte Carlo. QMC and randomized QMC are now in SciPy. And I have some homebrew R code just because this is to do the nested uniform scrambling. Most people want to use now the matrix scrambling from Matusek, but for research purposes, I like to have this one, and I'm using Dirk Nguyen's Magic Point Shop to make that happen. Okay, so it's fairly easy now to get good QMC software. Okay, so there's a lot of new directions in Quasi-Monte Carlo. I want to make a few shout outs, especially shout outs to some recent graduates working in this area. I was lucky to have two PhD students graduate in Quasi-Monte Carlo, doing Quasi-Monte Carlo just this year. So Sifan Liu is working on QMC for machine learning, variational inference normalizing flows, and Charlie Andral is also doing that. I think those are exciting new directions to put QMC into machine learning. I also want to give a shout out to Zexin Pan, who graduated with this past year. Zexin said, take the median of those replicates. Okay, so don't do 10, do 11. Take the median of 11. And for the Matusek scramble, most of the time, for a smooth function, the error is actually way better than n to the minus 3 halves. And it's only because there are outliers that you get this n cubed, n to the minus 3 variance. And the median trims off the outlier, and you can get a far better convergence rate if, under some smoothness. And that's been taken up by Gord and Lecuyer. So these two are, I think, quite exciting directions in Quasi-Monte Carlo. Also, there's some recent work using optimization or neural networks to find good low discrepancy point sets. So I'll point to Francois Clément, also Nathan Kirk and Konstantin Rush and others this is the neural nets paper that just turned up in PNAS, and Francois just defended his thesis last summer. So there's lots of interesting work going on. You don't have to use asymptotic formulas anymore. You can just try to compute it. There's new work trying to actually improve the confidence intervals and the uncertainty quantification, trying to understand those better. And there's new work on trying to automate the process of finding the really good formulation where you get the effective dimension down. Either make something smooth or make it bounded. Okay. So why wouldn't everybody use QMC all the time? Well, it comes with some hassles. And you can look at a hassle and think, yeah, that's just a speed bump. And somebody else thinks, actually, for me, it's a roadblock. And people look at them differently. You need to use inversion instead of acceptance rejection. So that's a bit of a hassle. Or it's much better to use inversion. You have to think of plan the whole n by d matrix you're going to use. So rather than just call R norm every time you need a new Gaussian, you have to kind of plan it out. It's a little bit weird. You might find that if you used 1,000 points and your neighbor used 512, they get a better answer than you. So Quasi-Monte Carlo has special sample sizes. Monte Carlo doesn't really have that. You shouldn't do burn-in or leaping unless you really know what you're doing. And sometimes people want to skip the initial point at 0, and that can actually make your convergence rate worse. So you're much better off randomizing instead. Okay, so those are just hassles that, they don't seem like much when you're doing the math about Quasi-Monte Carlo. They seem like a nuisance if somebody wants to pick it up and give it a try. Some hassles are opportunities. So improving the effective dimension. If you can make the effective dimension much better, you feel like you deserve a better answer. If you can't make it better, you feel like you deserve as good an answer as the person who could. So there's kind of funny thing where it takes some hard work or luck to make it really, really improve on MC. There's another feature that usually the best inputs are variable 1, 2, 3, and 4. So if you can organize your computation so that the first one is the most important one, then that's better. Okay, so important sampling with QMC, that's still a bit of a work in progress. It's very hard to get that right. The asymptotics are kind of clear, but you have to watch out for a better rate in n with a worse rate in dimension. And I think it's time for some new emphases, especially with machine learning. The old emphasis was making 100-fold improvement or in variance or getting a better convergence rate. I think on a huge problem, a 5 or 10-fold improvement would be very welcome. And then there's a bonus. If you're using QMC, you probably don't need control variance. QMC can soak up, in many cases, and I have a paper with Christian Lemieux and Fred Hickernell on this, QMC can do whatever the control variant was going to do for you. So you don't have to estimate that coefficient. Okay, so I'm a little over the time that I aimed for. Quasi-Monte Carlo can be used in Markov chain Monte Carlo. That would be a whole another talk. And I want to thank a lot of people. I want to thank all my co-authors and the NSF. I want to thank Sifan Liu and all the other organizers, and thank you for your attention.
Great, thanks a lot.